So next part of our problems is we're going to do a non-linear analysis lah. So non-linearity in finite element analysis can be divided into basically three lah. What I can find here, three. Number one is geometric non-linearities. Number two is material non-linearities. And the other one is actually boundary. Boundary non-linearities lah. For example, you have things like contact. Contact provides a lot of non-linearity. So we are going to do an analysis on material non-linearities lah, which is most common one. If you take a look at it, geometric non-linearities is then happens when the material needs to stiffen up in the direction of the load, and the load needs some sort of changes lah in the deformation. So this is an example of it lah, how the load changes as long when the structure changes, deformation change, right? The load direction also change lah. So you have a place where there is a stiffening on the structure or softening of the structure. So the response might be slightly different. The next one, which is material non-linearity lah. So material non-linearity happens when you have plasticity involved lah. Plasticity. So if you apply plasticity in your material loading, it's no longer a straight line. It's actually a straight line in the beginning, and then it flattens out, and then it fails. So material non-linearity, you can apply things such as plasticity. Next is contact non-linearities. When you apply contact problems, you will see much more non-linearity in the response itself lah. And when you solve non-linear problems, it is actually solving it incrementally, meaning it is solving it slowly and slowly and slowly. It will say that 1 second, but it's actually not 1 second lah. It's just a pseudo time, not real time lah. How to do that? Instead of currently we're doing static analysis, don't go here, you go to non-linear. Non-linear, and you choose static. So this is dynamic, this is static lah, choose this one. And then you need also change at the material model from linear, change to, for example, plasticity von Mises. And then you can do material non-linearity lah. Okay, let's do one analysis. So this one we can file, close, don't save, and then let's turn this one. This is a specimen. You can find this specimen in engineering materials lab. It is held at two places here. Normally you grip top and bottom, and then the tensile tester will move slowly and slowly down, and deformation will happen at your part lah. Okay, for the time being, let's do new study first, and then let's do a static analysis first, then later we'll compare. Static analysis. Let's define the material. What material is this? We can define any material lah. Let's say I am applying this to become, I don't know, aluminium, basic aluminium lah, 1060. Yield strength is 27 megapascal only, very low lah. So 1060 aluminium alloy. Connection, I have nothing here because this is single component. Fixture, I'm going to fix somewhere, meaning this one and this one is being gripped. and then I'm going to click OK, and then I can, instead of applying load, I have external load, right? Instead of applying force, you can also model motion. For example, in tensile tester, the bottom part will move, right? So you don't actually apply fixed loading, your loading changes. Let's say I can apply, instead of fixed geometry, I can click on advanced fixture lah. And then I can choose, for example, here and here. Listing the reference, I can choose front plane. And then I'm telling it is actually moving down. Can you see the arrow? Oh, that way, no. Not that way lah. That's actually this one code. No. So it's actually going down this way, okay. You can see the arrow going down. So I'm telling these surfaces, please go down by 0. Can I go 1 mm? 1 mm. You can even tell that. I am telling it, this surface go down by 1 mm. So I don't apply load. I can even do that. Instead of applying load, I'm applying a displacement boundary condition. So no loads here. Mesh, I can create a mesh. You can get away with a bigger mesh size. However, if you're doing final projects or anything important, you can improve the mesh size a bit. Improve meaning make it slightly smaller, much better accuracy lah. Can I run now? Run this. So I'm telling the model to go down by 1 mm. So I can get the stress lah. How much is the stress? Again lah, I hate doing this. But apparently it's a requirement. I can't change it to default. Change to general, change to mesh and discrete. So I'm getting something like this. So if you want to see deformation scale is 12.6. I can change this a bit. Never mind lah. What is the value we're looking at here? The value that we're looking at, let's do some probing. Pro tools probe. The value of the stresses here, 996. What else? 996. 996. Semua stress kat sini semua 996, 99982. So the stress that we are getting is actually 900 something. We forgot to do the material data just now. So this is the stresses I'm getting. 996. So this is not logical. Why? Because my material model is actually behaving this way lah. Yield strength. This is my material model. So if this were to be true, let's just sketch a bit here. This is my axis. This should be stress, right? This typically we assign it as strain. Currently tensile strength is 68. Yield strength is 27. So 27, they're linear, and then like that, and then it should feel like that lah. Linear up to here, 27.5, and then Over here is 68.9. Ini semua megapascal lah. So it should be behaving like this. What am I getting right now? Currently I'm getting 996. So now my material model, the behavior is actually like this. To the moon. MOON. Somewhere here. How much? 996 megapascal. So it's actually not true. So now we are going to do an analysis called non-linear lah. This one is called linear elastic. Currently we are doing non-linear. So let's try. It's quite quick. Keep the annotation. Let's go to your SolidWorks. Close it. Static, you can create a new one. File, new study. So no longer choose static, choose this one, non-linear, and then choose static lah. This one will be dynamic. This one is dynamic. Change to this one, static. Non-linear static, click on OK. So this thing will come out lah, non-linear, right? So you don't have to do everything again. Go to static and copy dah. Click this one. Hit shift, I think. Oh no, cannot hit shift. Click this one and then hit control. Fixed, reference and mesh. So I selected 4 items. How do I select it? I just hit control and then I drag it. Drag it to non-linear. So the whole thing has been copied lah actually. I don't have to do again. Fix also I don't have to do again. Reference geometry also no need. Mesh also no need. Semua dia dah copy lah. There's nothing else for me to do. I just have to hit run lah. Is it? No, I have to change something. Click this one. Material I have to change lah. Right click, edit material. Currently it is actually linear elastic, right? Now change this one to plasticity von Mises, and then click apply. So the moment I hit apply, I can close, and then I can run the analysis. So this message will come out. It's okay, show intermediate results. Click OK. You can hit more if you want to see the progress. Currently it's at 54%. No, currently it's at 3%. So typically it's going to be much longer lah compared to linear. Sometimes it fails in between. So gonna take some time. 25%. I'm not even halfway. It's using about how much? 1 GB of memory. If you look at here, solver iterative, time is 1. It's not actually 1 second, it's actually pseudo time. Pseudo time meaning not real time lah. Pseudo science meaning not real science. %75%. If you are just concerned on the linear part of your material, you don't have to do non-linear analysis actually. Okay, I'm done. 100%. Okay, so we are done. Let's probe. So if you probe, click here and then probe some values. Probe somewhere here, right? Again. Edit definition. Megapascal. General. Click on OK. Okay, let's probe it again. Probe values. I'm getting 27.5. Huh? 27.5 megapascal. Quite low. 27.6. 27.6 megapascal. Is this meaning it doesn't exceed yield strength yet, huh? 27.6. See, yield strength is 27.6. Meaning they're flat lah, they're flat line. Bukan jadi macam tadi kan. Let's screenshot. This is my current result. Paste it over here. So, currently it's like this lah. Only it will go up to maximum, which is the yield stress. Anything above that, it will maintain it as the yield stress. Yield strength 27.5. It's no longer like this, 1900 something. No longer like this. And you can even plot out what is the progress. Click here, response, and then you can see what is the value of stress on the parts. How to do that? Click on plot tool, click on probe, and then hit something, and then click this one, response. It will tell you what is the response that they are getting. Currently, the stress at this particular part, it's behaving like this. Behaving like that. Send to the back. So this is actually non-linear lah. So you can see clearly what is going on with the material model. So the material model behaves linear, and then flatline, plastic region. So if you have real material data, for example, another thing that I can do here, before I forget, I can click compare results. Since I have two analyses, I can click compare results, change this one to all the studies, and then I can turn off whatever I don't want. For example, I just want to compare stress to stress. Click on OK. So it will show you next to next, window to window. However, bear in mind the scales are different. So I can exit now, exit stress, exit compare. So if you have real data, for example, the one that you test in the material lab, things like this. You have real Excel data, forces versus time, and then you've got the elongation. You need to change it from engineering stress to engineering to true stress, and also engineering strain to true strain lah. How do we change this data? Do I have it here? There's a way to do it now. You can use a formula also. And if you plot in Excel, your material model will behave like this. Now, if you really plot it, by right, you should change this one lah. Change the ones to non-linear elastic, and then create a stress strain curve. And then you have to paste from your Excel points all these things, and then your material data, you will get exactly the response. You will get exactly what you did in your experimental lab. Okay.